All right, in this section we're going to be taking a look at the graphs of exponential and logarithmic functions. And so the first question that we really need to ask is really, what is a logarithm? And by definition, a logarithm is simply an exponent. And we'll see why here in just a second. So exponential equations and logarithmic equations are inverses of each other, and that is the reason why we are looking at these two functions in the same unit, because in order to solve a logarithmic equation you need to convert it to an exponential, and vice versa. To solve exponential equations you have to convert them to logarithmic. It's kind of like when you have x squared equals 16. You solve x squared equals 16 by taking a square root, because squares and square roots are inverses of each other. Same thing with exponential and logarithmic. They are inverses of each other, and so they are needed in order to solve the equations. Graphically, this means that they are reflections of each other over the line y equals x from our information that we did on inverses a long time ago. All right, so if we have this right here, x is equal b raised to the y, this is an exponential equation. The letter b stands for base. So anytime you have some number raised to a power, this number that's being raised to the power is going to be the b, is the base. And there's a conversion that will take us to a logarithmic equation, and that is going to be log base b of x is equal to the y value. All right, so this is our conversion here. The base right here is also the base right here. This equation is read as log base b of x is equal to y. So if we think about the y value, the y is an exponent. Well, look at our equation here. Y is equal to this logarithm, which means by the definition that we had up here, a logarithm is an exponent or equals an exponent. All right, so now we're going to be using that conversion to be able to convert some of these equations into logarithmic equations. So the first one is 3 squared is equal to 9. That would equal log base 3 of 9 is equal to 2. So if we remember our conversion from on the other page, we had x is equal to b raised to the y, which converts to log base b of x is equal to y. All right, so we can identify our different parts here. The 3 here is our base value b, so that becomes log base 3, which is what we have here. The number that comes after the log is our x value, and the x value was what it equaled, which was our 9. So we have log base 3 of 9 is equal to, and then we have the y value right here. All right, so the next one, doing the conversion, this is going to be log base 4 of 64 is equal to 3. The next one, log base 25 of 5 is equal to 1/2. And then lastly, log base 9 of 1 over 81 is equal to negative 2. Now, remember, when you have a 1/2 power, that means the same thing as a square root. So 25 to the 1/2 power means square root of 25, which is equal to 5. And then the other thing to pay attention to is when you have a negative exponent. A negative exponent flips your number. So this becomes 1/9 squared. After you flip it, the exponent then becomes a positive, and then this converts into 1/81. All right, so the next thing we're going to do is go from a logarithmic equation to an exponential equation. If you think you can handle these, go ahead and pause the video and then work through the problems, and then unpause it and see if you got the right answers on these. So go ahead and take a pause on the video and work through these problems. Write them down and work them. All right, so let's take a look at our solutions here. You're going to have 2 raised to the 4th is equal to 16. 10 to the 1st power is equal to 10. And this 10 right here is the base value 10 right there. Then we have 3 raised to the 0 power is equal to 1. And 10 raised to the negative 1 is equal to 0.1. So now what we want to do is we want to evaluate our logarithms. What we have is part of our equation. So when we are evaluating a logarithm, really what we're trying to do is figure out the base number 2 raised to what power is going to give us 16. So this is how we're trying to think of this. 2 raised to what power is going to give us 16, and that would be the 4th power. 4 2's multiplied together are going to give you 16. So the next one, you're trying to think 5 raised to what power is going to give us 125, and that is 3. 5 to the 3rd power. So log base 5 of 125 is 3. All right, so the next one, we're trying to figure out 9 raised to what power is going to give us 3. Well, one of the things you need to recognize is that 3 is the square root of 9. So that means we would raise 9 to the 1/2 power, which means square root. And the last one is 9 raised to what power is equal to 1. And that would be the 0 power. Now, one of the things you need to think about on this one is it really does not make any difference what your base value is. If you are taking the log of 1, any number to the 0 power is going to equal 1. So if you're finding the log of 1, the answer is always going to be 0. Doesn't matter if it's 9 to the 0 power or 4 to the 0 power or 50 to the 0 power. The base number does not make any difference. So that's going to lead us into some properties that we can look at. The first property right here says the log base a of 1 is always going to equal 0 because it does not matter what the base value is. A to the 0 power is always going to equal 1. So now the next one is log base a of a, which is always equal to 1. So that means, for example, log base 2 of 2 would equal 1 because 2 raised to the 1st power is equal to 2. Or you might have log base 5 of 5, that's equal to 1. Log base 123 of 123 is equal to 1. So as long as these two numbers are the same number, this is equal to 1. All right, and the last one here says log base a of a raised to the x power. So these two numbers need to be the same number. So if you think about this, this would be a raised to what power is equal to this, a to the x. Well, in that situation, your bases are the same, which means what we're looking for has to be the x. So that gives us an x right here. That confirms that if you have log base 2 of 2 raised to the 15th power, means that you do not have to figure out what 2 to the 15th power is. That's a very large number. As long as these two numbers right here are the same, our answer comes out to be simply the exponent. So this would equal 15. If you had log base 9 of 9 raised to the 7th power, that would equal 7. It's just equal to the exponent, as long as the base and this number are the same. All right, so the next thing we're going to look at is sketching a graph of the equation of y equals 2 raised to the x, and then y equals log base 2 of x. All right, so we're going to start out with y equals 2 to the x power. So if we just kind of make a table of values here, if I use 0, 2 to the 0 power is equal to 1. If I use a 1, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power would be 8. I'm going to start getting numbers that are larger than my graph, so I'm going to stop on those. Now I also want to plug in some negative values. So 2 to the negative 1. Remember that a negative exponent tells us to flip this, so it becomes 1 over 2 to the first power, or 1/2. Negative 2 would be 1 over 2 squared, which is 1/4. So plotting these points, we have 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4, and the fractions are just going to get smaller and smaller and smaller, which means, but they're still going to be positive. They're still going to be more than 0. They're not ever going to quite equal 0. Therefore, the x-axis is an asymptote for us. All right, so now we're going to take a look, and this one was y equals 2 raised to the x power. All right, so then the next one we're going to be looking at is going to be y equals log base 2 of x. And so we want to plug in some numbers for x that are going to be friendly numbers. And so if we think about the numbers that we're going to plug in here, 0, can we use 0? Well, no, we cannot, because we cannot raise a positive 2 to a power and get 0 out of that. If we try to think about this over here, 2 raised to a power to get 0 is not going to work, because if you put a positive number in here, you're going to get a number larger than 0. If you put 0 in here, 2 to the 0 power is 1, so that's not equal to 0. If I put negative values, well, all that does is flip the numbers so they become fractions. They're still not going to be 0. So there's nothing I can make in the exponent to give us 0. All right, so we can't use 0. We also cannot use negatives, because 2 raised to a negative, 2 raised to a power is not going to be a negative number. So we cannot use negatives either. All right, so what can we use then? We can use positive numbers. Let's go ahead and start with 1. Log base 2 of 1. you remember, that was one of our properties. The log of 1 is always 0. All right, so let's use a 2. Log base 2 of 2 is equal to 1. That was another one of our properties where those two numbers were the same value. The next friendly number is going to be 4. That would give us log base 2 of 4. So that means 2 raised to what power is equal to 4? And so the solution would be 2. All right, and larger than 4, I'm going to start getting off my graph. 8 would be another number, but that's beyond my graph. So let's say 1/2. Well, 1/2 would give us a negative 1, because log base 2 of a half means 2 raised to this power would equal 1/2. 2 to a negative exponent flips it, so that becomes 1/2, the first power. All right. And likewise, we could use a fourth, which would be negative 2. So let's plot our points. We have 1, 0. We have 2, 1. 4, 2. A half, negative 1. And a fourth, negative 2. And we said we cannot put 0 in, so the y-axis is a vertical asymptote for us. And our graph looks like this. Now you'll notice that these two graphs are reflections of each other over the line y equals x. All right. So just coming over here to answer some of these questions, based on the logarithmic graph, which is our blue one, you can only take the log of what kind of numbers, and that would be positive numbers. And then based on the exponential graph, if the base value is positive, then the value of the function is going to be positive. A positive number raised to any power will always be a positive number. Now, what I want you to think about is, in a little bit, we're going to get into the graphs. And this point on the logarithm graph and this point on the exponential graph are the 2 points that we are going to be transforming and doing the shifts and the stretches, compressions, reflections, and all that stuff. All right, the next thing I want to talk about is the irrational number e. And so e is an irrational number. The word ratio implies a comparison of two numbers, which we usually think of as a fraction. IR as a prefix means not. All right, so e is an irrational number, which means it is not a rational number, which means cannot be written as a fraction. Now, other numbers that are irrational that you know of, pi is an irrational number. Square roots that do not come out evenly, for example, square root of 3 is a decimal, that is an irrational number. Those cannot be written as fractions. And so the way that we come up with the value of e, which, by the way, the value is approximately 2.71828. If you just remember 2.7, that'll be enough for most purposes. That's our value of e. So e is a constant. It has a specific value to it. This is how we achieve that value. Just simply put, don't know really what most of these things. You don't know what most of these things mean. An exclamation point in math is called a factorial, and 0 factorial, by definition, is equal to 1. You'll look at that a little bit later on in your math career. 1 factorial is also equal to 1. 2 factorial is equal to 2 times 1, which is 2. 3 factorial is equal to 3 times 2 times 1, which is 6. And 4 factorial is equal to 4 times 3 times 2 times 1, which is 24, and it just progresses like that. So when you think of 1 over 0 factorial, that's the same thing as 1 over 1, which is 1. 1 over 1 factorial is 1 over 1, which is 1. 1 over 2 factorial is 1 over 2. 1 over 3 factorial is 1 over 6. 1 over 4 factorial is 1 over 24, and it just keeps on going forever from there. And if you add up all these fractions, it just gives you this decimal here, which does continue on. And now, I mention all this because there is a special type of logarithm called a natural log. And a natural log is written as y equals ln of x. And a natural logarithm is a logarithm with a base value of e. So y equals ln x, which means natural log of x, is equal to log base e of x. Those two things right here, these two equations are the same equation, but we don't ever write it like this. We don't ever write log base e. It's always written as natural log of x. Now, by and large, all the equations that we use in calculus are going to be natural logarithm equations. Very seldom are we going to be using what are called common logs, or LOG. The vast majority are going to be natural log of x. And so you need to become very familiar with natural log. Just means log base e. All right, so looking at transformations here, what I would like for you to do is go ahead and pause this video and see if you can fill in these transformations based on the transformations we have done in the past on other functions. All right, so here are the letters. Now, the C that I have right here is not this C, it is this one right here. This is the base of our exponential equation. And the base value is not a transformation. The base value is part of your parent function. And then we have a logarithm graph over here, and log base 2 is what I have, but it doesn't really matter what the base is. The same thing with same transformations hold true for a natural logarithm as well. So these are really all the same transformations that we've done before. So go ahead and pause the video right now, fill in your transformations. Over here is going to be the condition for whatever the letter is. And all right, then go ahead and pause and then unpause in a little bit to check your answer. Okay, you can go ahead and check your answers here. I think everything is pretty much self-explanatory. Remember that anything that happens inside parentheses is a horizontal effect on your graph. The parentheses are the exponent on the exponential equation. So anything that happens in your exponent changes your graph horizontally. All right, so now we're going to identify some transformations here. Going from f of x to g of x, we have the negative, which is a reflection over the x-axis. We have the minus 5 up here, which is a shift to the right 5. And then this is up 1. All right, so now going from f of x to g of x over here, we have a negative, which again is a reflection over the x-axis. But we also have a negative here in the exponent, which is a reflection over the y-axis also. And then we have a shift down 6 units. All right, so the next one, we're not going from the parent function, but we are going from the graph of f of x to the graph of g of x. So what we want to think about here are our shifts. Okay, so this one has been shifted to the right 3 units. This one has been shifted to the left 1 unit from your parent function. So if we're going from a graph that was shifted right 3 to a graph that was shifted left 1, to get from here to here, you're going to have to go left 4 units. So we've got a shift left 4 units. All right, so now this one was shifted down 4 units, and then this one is shifted shifted down 3 units. So in order to go from down 4 units to down 3 units, you're going to have to go up 1 unit. So we've got to go up 1. All right, so then we also do have a negative up here, and so it was going from a positive to a negative, so there is a reflection over the y-axis as well. All right, so the next one, we're going from the parent function f of x to g of x. So we have a negative, which is a reflection over the x-axis. We have a 2, which is a separate transformation. That is a vertical stretch by a factor of 2. We have the 3 here, which is a shift to the right 3. And then we have the last one, which is up 5 units. All right, so now we have some natural logs. And again, we're not going from a parent function, we're going from a transformed graph to a transformed graph. So the first one here was shifted left 2 units. This one is shifted left 3 units. So to get from here to here, you're going to have to go left 1 unit. All right, so the next one, this one was shifted down 3. This one was shifted down 1. So to go from here to here, you're going to have to go up 2 units. All right, so the next one goes from the parent function to this one. And we know the plus 1 here on the end, that's the up 1. That's fairly easy. And we have a 3 in front of your x, which is a horizontal compression. By a factor of 1/3. Remember, it's the reciprocal value. And then, because we have a 3 in front of the x, you got to remember that we need to factor the 3 out of both of these terms. So what we have right here is really a shift to the right 3 units. It's not a shift to the right 9, it is a shift to the right 3 units. All right, so if your base value c is greater than 1, so what we've got is y equals c, and your exponent is less than 0, so we're going to have minus x. So if we have the equation y equals c raised to the negative x, where c is a number larger than 1, so let's think of a number, let's just say 2. 2 raised to the negative power. Well, what a negative exponent does is flips the number. So you can think of this as y equals 1 over 2 to the x power. Well, that means that when your x value gets bigger, your denominator is going to get bigger. And if your denominator gets bigger, the value of your fraction gets smaller. So what's going to happen is your graph is going to approach 0. For example, your fraction might be 1 over 2, and then 1 over 4, and then 1 over 8, and then 1 over 16. So as x gets bigger, your denominator gets bigger, which means the value of the fraction gets smaller. That makes this an exponential decay situation. Now, this can also be written, if you have 1 over 2 to the x, this can also be written as 1 over 2 and then raised to the x power. These things are equivalent to each other. All right, so the next one says if your base value c is greater than 0 but less than 1, so if we think of a number more than 0 but less than 1, so let's just call it a half, and your exponent is less than 0, so we're going to have a negative x in your exponent, then what are we going to have, growth or decay? Well, once again, the negative exponent right here is going to tell us to flip the fraction. So this is equivalent to y equals 2 over 1 raised to the x power. Well, now as x gets bigger, you are going to get a bigger number. 2 to the second, 2 to the third, 2 to the fourth. The numbers just get bigger and bigger and bigger, so that's exponential growth. Next, if your base c is greater than 0 but less than 1, so again we'll call it 1/2, and your exponent is greater than 0, you will have an exponential what? So we have a positive exponent. Now, as x gets bigger, the value of your fraction is going to get smaller. For example, x to the 1/2 raised to the first power is a half. A half to the second power is a half times a half, which is a fourth. Third power will be a half times a half times a half, which is 1 over 8. And then it keeps on going like this, which means your fractions are going to get smaller and smaller and smaller the bigger your exponent gets. So this is going to be an exponential decay. And then the last one says, is y equals e to the x exponential growth or exponential decay? It is growth because e is larger than 1. And you're raising that to a positive exponent. All right, so the next thing we're going to do is sketch a graph from an equation. The very first thing you want to do is figure out, do you have an exponential graph or a logarithmic graph? And these two are going to be exponential because your variable is in the exponent. Now, exponential graphs, if you'll recall, let me put it in green here. Exponential graphs cross the y-axis at 1 and went like that. That was our parent function. All right, so the point that we are going to transform is going to be that point 0, 1. And first thing that we can do with this is that point has we've got a negative here, which means we're going to reflect it over the x-axis. So reflecting this over the x-axis will put us at 0, -1. All right, then we have right 5 units, which will put us right here. And then we have up 2 units, which will put us right here. So we are now going to be at 5, 1 for our coordinate. Now, let's think about the asymptote. The asymptote for your exponential parent function is the x-axis, y equals 0. The only type of transformation that will move a horizontal asymptote is going to be a shift up or down. And because this is shifted up 2 units, that means our asymptote is going to also be shifted up 2 units. All right, and our graph is going to go like this. So if you think about what has happened down here, your parent function started out like this, but there was a reflection over the x-axis, which means our graph is now going to go like this. And so what we do is we take this graph here and we shifted this one right 5 units and up 2 units, which gave us this blue graph right here. All right, so the next one, still looking at the parent function at 0, 1 point, and we're going to move it left 3 units and down 4 units. So left 3, down 4 is going to put us right here. All right, so now the asymptote is also shifted down 4 units. So down 4 units for the asymptote would put it right here. Now there were no reflections on this one, so our graph looks very similar to the parent function and will go up like this. Now, yes, I could get a more accurate graph by plugging in a lot of numbers for x, but really what I'm trying to get you to understand here are the transformations, and so I'm using 1 point to transform and the asymptote, and so we can get a relatively fair sketch out of that. All right, so the next ones we're going to look at are logarithm graphs. And so the logarithm parent function, I'll just sketch that here, went through the point 1, 0 and came up like this. So that was what our parent function looked like for a logarithm. All right, so now what we have here is a reflection over the y-axis. So if we take the logarithm graph here and reflect it over the y-axis, that's going to make it go this direction. That also means that this point is going to move to here. It reflects over the y-axis. And we also have to move that point up 2 units, which puts it right here at -1, 2. All right, so -1, 2. Now, on logarithms, you have a vertical asymptote. The only transformation that is going to move a vertical asymptote is a left or right shift. Shifting up and down does not move that asymptote. There is no left or right shift on this, so we don't have to worry about that, and so our graph is just going to go in this direction, similar to what the graph was here, except we shifted it all up a couple of units there. All right, so the next one, if we start out with our parent function point right here, we're going to shift it to the right 4 units, so 1, 2, 3, 4 units, and then we shift it down 1 unit, which will put us right here. All right, so now we do have a shift in our asymptote. Asymptote is going to be shifted to the right 4 units. And those are the only transformations, so there's no reflections to worry about here, giving us a graph that will look similar to this. All right, so then the next one, these are the last two problems here. We're going to write or build an equation for each of these graphs. So the very first thing that we want to look at is what type of function is it? Is it an exponential equation or is it a logarithmic equation? They look very similar to each other. If you look at these two graphs, they look very similar. So the way that you tell is by the asymptote. If you have a vertical asymptote, that means it is going to be a logarithm. If you have a horizontal asymptote, it is an exponential equation. All right, so what I'm giving you is the information that the base value is going to be 2. And like I said here, the graph on the first one is going to be a logarithm. So we're going to call this log base 2 to start out with. Now on your logarithm, remember the parent function point was at 1, 0. That point has been transformed by shifting to the left 2 units and up 4 units. So left 2 and up 4. All right, so when we do that, that's going to give us an x plus 2 and then a plus 4. Then we also have a reflection over the x-axis, which is a negative out in front of our logarithm. All right, now the next one is exponential, and the base value once again is 2, so we're going to have 2 raised to some power. And if you think about the parent function point right here, well, that point has simply moved down 5 units. So what we're going to have then is just a minus 5 on this. All right, well, one of the things you'll also notice is that your asymptote went down 5 units, which just confirms what our transformation was right here. Now, this is an exponential decay graph, which means our equation or the graph was reflected over the y-axis, which will put a negative in the exponent here. So this becomes the equation that we have built.